in this case, there was another set of fractal division that was going on in the middle. And when I looked at it closely, I realized that that set of information was the exact same structure of division, those triangle divisions of space, or these tetrahedron division of space, but in this case, pointing in the opposite direction, going inwards towards infinitely small. Never mind the fact that if I overlaid the octahedron part of the 64 tetrahedron grid over top the crop circle, it was a perfect fit. This compelled me to continue to study these things, and as I was studying advanced physics and continuing to advance my theories, and I realized that there was eventually crop circles that were perfect representations of the 64 tetrahedron grid that were emerging in the crops of England. And then vector equilibriums coming out of the crops of England with singularities at their center, including the information about the boundary generated by the tetrahedrons, so that if you knew that each tetrahedron generates its own boundary, then you would add them here and generate this other geometry which has been popularized as the seed of life, and then a crop circle to tell you you've decoded right. And so this was like a code that was being given. I was very excited about that. I continued to study it, and there was very much information that was coming out of the crop circles that had to do with fractals, the way those spheres, okay, each boundaries of the tetrahedrons divide. Here we can see it in another crop circle where the central part of the sphere divisions it has these crescent that seem to indicate rotation, angular momentum, which is what we're going to get into in a minute or after lunch. And then that division of space was fractalized over the field. And then eventually even structures like this that showed these spheres dividing in a rotational pattern. This one, crop circle, right across from a very well-traveled highway, which has Stonehenge on the other side. Okay? Very large crop circle that appeared. And then even larger ones, like so, that showed that spiraling division of space, that dynamic. And now I was starting to really link into I believed I had found a fundamental structure of equilibrium for the vacuum state. Now I had to understand the dynamics that fundamental structure generated in the field equation, the dynamics of it, not the static view of it, but the dynamics of it, the angular momentum, the rotational part of it, the field equation that emerged from it. Because remember, the vacuum state geometry would be the structure that goes towards infinitely small, that collapses into singularity. There's the other side of the equation, the feedback, which is the radiative side, which has all these energy levels and all these dynamics in it, and that had to match to the geometry of space. from this seed, how would the field get generated. I had the static model of the structure of the vacuum, but that was only the vacuum state moving towards infinity. I didn't have the vacuum state generating the electromagnetic radiation from that division of the space. And so I started to, realize that they had to be angular momentum, they had to be spin involved in the space-time manifold to generate that boundary. In order for the vacuum to generate a boundary, it had to have some kind of shearing, and in technical terms, this is called shearing modulus, that would divide the space, that would fracture the structure at very specific intervals. And I was thinking about it, and I was studying and then eventually it came to me, and I realized, and it came to me in different ways. I realized that they had to be gyroscopic reasons. They had to be gyroscopic dynamics of the angular momentum of the metric of space. And I started to study gyroscopic effect, angular momentum and Coriolis forces and all this. And I started to study deeper and deeper in physics, and especially in Einstein field equation, how we dealt with rotation and angular momentum. And I realized that in many cases, we in general try to avoid spin and angular momentum. We try to make things freeze up so that they can get simpler and easier to map out. But when we do that, then we most likely lose a very important component. And then I realized that we had done that with something very, very fundamental. And I started to study how Einstein came to his equations and how his equations were solved. So Einstein did this. He basically, in general relativity, he extrapolated that gravity may not be an internal force of an object, but instead the force of that object applied to the structure of space-time itself. And the way you can describe it simply, imagine a surface of a trampoline. And that trampoline has a big ball, a heavy ball on it. Now the surface of the trampoline around the ball is going to curve like this, and that you could call space-time curvature. And if you took another ball and you put it in the trampoline, it would want to rotate or roll or have an orbit around that first ball because of the space-time curvature around it. This is the typical visualization that you get from space-time curvature. When Einstein wrote this idea of this metric, curving and creating this space-time curvature, he didn't solve it. He just threw out the idea, basically. And he published it, and he thought it's going to take a while before this is solved because it's really complex. But there was a German physicist on the Russian front that got a hold of his paper. His name was Karl Schwarzschild. And he thought, hey, let's try solving this. So while dodging bullets and being sick and everything, he solved Einstein field equations. And when he did so, he simplified the equations, he simplified the models so that it would be easier for him to do a first approximation. And the way he did that is that he assumed that the object had no angular momentum, no rotation. Okay? So he solved the equation for something that's not spinning, because it was the first approximation. He sent the result to Einstein, and Einstein was so impressed that it was already solved, that a solution had already been found. He right away sent it to Prussian Academy and got it published.